It's just to get a temperature check, really. So we're looking at now structuring it for next year and what we can do sort of these last few weeks on the run to obviously sort of exams and final assessments and so on. So it's just to get a little bit of feedback just in terms of have you engaged? If not, would it fit better in terms of what else they can do? So yeah, it'd be great if you just fill it out and I'll just collect them at the end. That's why it's okay, because I liked.
After I read the extension, I was like, thank you. Like write everything on here. It feels really like satisfying. Like things like also like all over the place. The writing. I never thought of doing that until now.
I have a list of making stuff because I'm not up to do it. And then I get really stupid when I forget something and I want to remember it.
This tea is clear, man.
You went there for 5 minutes.
It's like red berry or something like that. I usually drink green tea. I just like green tea, but I guess like I never had like really like good green tea.
Yeah.
So where do you live? Okay. If I forget to bring them back to you, just email me. Okay, so this morning we are going to look at file formats, images and compression. So it's quite a technical lecture and some students in the past have a bit struggled on it. So since we are not too many of us, feel free to ask questions if you feel that at some point it's going too fast. So this lecture is part of the theme IT Fundamentals. And you can see that our 4 themes are filling up quite quickly. First, a bit of feedback about activity 15. So I got 41 submission and 40 passed. So it looks that people who put the effort achieved. Some people enjoyed it. Some people ask a few questions. So is it easy to create an operating system? I would say it's really tough. It's not something you will do in a weekend. So millions of lines and very big teams. A personal question: which operating system do I like the most? And actually the one which is supported by my IT team. Okay. In Kingston, they are very good with Windows. I have a problem, I pick the phone, they sort it out for me. So I choose Windows. In my previous institution, it was Linux, and I was happy to be Unix. I mean, personally, I don't see major differences, especially when you are using PowerPoints, Word, those type of applications. It doesn't really matter. if you use specialized software or if you are dealing with supercomputing and so on, maybe the choice is quite critical. But for most Office-based applications, I think just follow the flow and get the support you can get. Most of the questions I had were about Linux. I guess most of us are used to use Windows maybe every day. So first of all, I suggested a piece of software to connect to your Linux server, the one which is hosting your website. So some people found it a bit tricky to use it, but eventually they managed. So it's good. You know, that's what I want. I want you to find it a bit challenging, a bit tricky. I want you to learn in the process, and at the end of the day, maybe with the support of your mentors, you manage to pass the obstacle and complete the task. As I mentioned initially when I set this activity, some hosts don't want you to access their Linux server. They are afraid of you breaking everything, okay? And maybe they don't have a support service which is quite up to scratch, so they don't want their customers to do things and then call them and ask them to fix them back. So they have a policy of just not allowing anybody to get access to the server directly through software like Putty. So that's a shame, but so generally when you try to connect using Putty, you get an error message like connection timed out. Okay, so that means you are in that situation. So what to do, because you still have an activity to pass. So there is an option, is that on the web you will find some Linux emulator. Okay, so they pretend that you are connecting on a Linux machine, so it's an application. And you can use that application and enter Linux commands and so on. So it's not your Linux environment, it's a Linux environment. But for our purpose, it's good enough for you to practice a little bit. So people would like more about Linux, and you will not do more this year in IT Toolbox, but in the following years there will be more. People would like to know more about virtual machines as well, and again, it's a more advanced topic that you will see next year. Some people, obviously in the activity, I ask you to copy the output of some Linux commands in the sheet for electronic submission, and some people had troubles doing that. So first of all, I would suggest try to use that command. The superior signs allow you to copy which is displayed on the screen to a file. Okay, so if you watch, you display your directory, automatically it's copied in the file, so then you can open the file and do whatever you want with it. Just make sure that you have the right to create files and write into files, okay? Because as you will discover if you haven't done the activity yet, Linux is quite secure. You have a whole system of priority accesses, and you need to make sure that you have the right to create files and write into them. Some student told me that one of my questions was a bit ambiguous. So I'm asking, Linux is very popular on servers and supercomputers, but Windows is more for PCs. What is the reason of that situation? And so the student asked, are we interested in the Linux situation or the Windows situation? And I'm more interested in the Linux situation because that looks a bit odd, but I can understand that the question could be read the other way as well. And I think that's it. So just to keep us going, we are going to use the clickers. So as you have seen in the world of operating system, usually, how can I reopen? Usually the mouse is not very present, and one use the keyboard. Why is my phone closed? Okay, I don't know what's happening. Okay, so we are going to do it the old-fashioned way. Okay, so we are all using QWERTY keyboards, except if you are using a foreign keyboard, because it looks like every language has a specific type of keyboard. But all of those keyboards have a strange order in the letters. You know, it's not the alphabetic order as could be a big reason. And so the QWERTY keyboard is coming from a long time ago, so 150 years ago almost. It was adopted by Remington. And what was the reason to choose that order of the keys, okay, instead of typically the alphabetical order? So is it because it's supposed to be more ergonomic, to allow you to type quicker? Is it just for a technical reason? When you were using the old typewriters, you had the different keys and sometimes they would jam. So you would make sure that the letters are all mixed up so that people have to type very slowly so they don't jam. Was it designed to translate efficiently the Morse code, which is also a different code with a different order, or was it just the name of the pet of Remington? So who is voting for number 1? Not many people. Number 2? Yeah, small majority. Number 3? Number 4? Okay, so I guess people voted 2 or didn't vote. Okay, so that's the correct answer. Yeah. So the keyboard we are using today was designed in order to be the slowest, least efficient keyboard, so that there was no jamming when you would type between the. So it's quite interesting that a decision was taken 150 years ago for a reason that doesn't exist anymore, and we are still using those keyboards. So that's interesting how technology evolves, but some cultural things are still there and maybe keep us a bit behind. Oh, the polling is now open. Okay. Hopefully it will work next time. Okay, let's go to our topic. File formats, images, and compression. So, as you know, a computer file is a storage block which allows you to store data on your computer. So each time you save a document, you create a file. And those files have suffixes. Okay, so here typically we have PDF, docx, pptx, and I guess you are very familiar with those suffixes. So as soon as you see the suffix, you have some idea about what there is in that file, or some kind of what type of file it is. But there are hundreds of suffixes, many that you will not know. And also we want to know a bit more about what is behind those suffixes. So first of all, it tells you what kind of file it is. So if you want to open your file, you know which application you should be running. Obviously now on modern systems, they try to recognize it automatically, so you just double click on the file and the application is launched automatically. But also what is maybe more important is that it's associated with some kind of standards. Okay, so if you are writing a file with such suffix, we are expected the information to be organized in a very special manner. Okay, and those formats, they can be proprietary or free, and they can be unpublished, so only the maker of those files know how they are organized, and nobody has a clue about how it's organized. So if you don't buy the right piece of software, you cannot open it. Or some others are open. Okay, so we know exactly how the information is organized. So you are free to create your own piece of software in order to interpret that information. And here is a list of a few more file extensions. So if we look, for example, at the HTML format, that we have spent a bit of time on that one. So as soon as a file has suffix HTML, we know that the organization of that file means that you are going to get the HTML tags, you are going to get the body tags, and so on. Okay? Otherwise, the file is not going to be interpreted as a HTML one. Okay, so that's general structure of what you would expect to find in a HTML file. So now let's look at the text files. Okay, let's say that I want to store a sentence, hello world, and I am going to store one with Notepad and another one with Word. Okay, so in both I open the two applications, I write exactly the same text in both of them, and I want to know what will be the difference in terms of storage. So one option is I'm entering the same information in both documents, so the file will have the same size. Okay? Or I could say, yeah, but you are using Notepad, which is a free, boring piece of software. On the other one, you are using Word, which is made by a commercial company, a big multinational. So maybe they are able to optimize the file better. So they will be able to squeeze the information in a better way and create smaller files. Or maybe it's going to be the opposite. The file in Word will be 10 times bigger, or maybe 1,000 times bigger. Okay. So, has everybody voted? Let's see what are your results. So that's quite interesting. There is no clear view on what has happened. Okay. And so it's 1/3 for A, 1/3 for B, 1/3 for C, and hardly anybody for D. And the correct answer is D. So didn't do a very good job here. Okay, so if we compare the text format and the Word format, which is in this case .doc.x. So here is my document in Notepad. Here is my document in Word. Okay. So let's look at the actual document I've created here. So if I look at the size of my notepad, it has 12 bytes. Okay? But my operating system, which is Windows in that case, doesn't create files smaller than 1K. So the actual size on my hard disk is 1K, but the data is stored in 12 bytes. Okay? And 12 bytes, hello world must be 12 characters. So 1 byte per character, that's what we saw when we studied the ASCII scheme. Yeah, you remember a few months ago. So that's the normal expected size. So now if we look on the other side at my Word document, it has 2,624 bytes. Okay? So, which is 1,000 times bigger. Yeah. The good thing is that since it's stored by multiple of 1K, you store it 2.3K, that's 13K, so there's not much waste. Okay. So indeed, the Word document is 1,000 times bigger than my Notepad document. Anybody has any idea? Yeah?
Because of all the formatting that goes into a Word document?
Exactly, because in the Word document, it's not just the letters which have been stored, but it's also what kind of font am I using, what is the size of the text, what is the color of the text, has it been centered, all that information, which what a word processor is about, is equally stored in my file. Okay? So obviously when the files are very short, all that environment information use a lot of space compared to the actual text. Okay, so we need to make a very good difference between a text file and a file created by a word processor. There are two very different types of things. One, they store characters. The other one, they store text. They store sentences with colors, everything you want. Okay? But it's good that you have discovered something you didn't know about it. Okay, so that's my Word file. Okay, if I open it using a text editor, that's how everything is encoded, and you can see that it's not ASCII encoded. It's a binary format. So it's very important to understand how the information is organized. So that's why if you are using some software like OpenOffice, so the free version of Word, they need to do some kind of reverse engineering. How does Word store their file and then try to interpret that and display it as actually the content of a Word document. So that was about text, and I don't think there is much more to say about text, but graphics are much more interesting. Yeah? So first of all, there are two families of graphics. There is one which is called the raster graphics. Okay? And so in this case, an image is basically a collection of pixels which are organized in a grid. Okay? Does anybody know what pixel mean? And it's a strange word, okay? It's a modern word as well. Didn't exist 100 years ago. So what does pixel No? So I think pixel is called, it's a portmanteau. So basically you take two words and you bring them together. And the two words are picture and element. And become pixel. Okay, so you've learned another very important thing today for your next pub quiz. So a pixel is a picture element. Okay, so your picture is divided into small squares, and those squares are the pixels. And then you have another way of describing, of creating a graphics, is using vector graphics. Okay, and in this concept, in this context, an image is not anymore a set of points; it's a set of shapes. Okay, and to illustrate that, here is, for example, a circle seen as a raster graphic. Okay? If you zoom in your circle hard enough, you will see that actually it's not a circle, they are just pixels arranged in a way which looks like a circle. Whereas in vector graphics, you are not drawing every little square, you are just saying what I want to display is an object which has this center and this radius. And that's the way you define your circle. While here you need to define every single pixel. Okay? So it's very different. Which means that when you are displaying raster graphics object, when you start zooming in and in, you will see that the resolution of the image is not holding. At some point, you can start seeing all the single pixels because it was designed for a given resolution. Okay? You cannot zoom in as much as you want. Whereas the other one, it's not a problem. I gave to the computer just a formula. Draw me a circle. You zoom in, draw a circle using the space you have. And each time, you will get a fantastic resolution. Okay? So vector graphics is much more powerful than raster graphics. So raster graphics is typically when you are using some software like Paint or Photoshop. Yeah? So you are working at the pixel level. On the other hand, when you are using applications like Illustrator, CorelDRAW, or maybe PowerPoint, here you are working in the vector graphics environment. So here an example, here is a picture. Okay. So how was created that picture? Using pixel or using vectors? Okay. If we zoom in, and you get something like that, clearly it was created from pixels. Yeah? So from far away, everything looks nice. As soon as I zoom in, I start seeing the picture, and I cannot read what was on the label. If it was using vectors, it does remember that actually here what I wrote, it remembers the text I wrote. You know. It remembers a higher level, it remembers shapes, it remembers text, and so on. So wherever the resolution is going to display the information. It's not based only on pixels. Okay, so the question is, vector graphics is, as I demonstrated, much more powerful in terms of quality. So what are the type of graphics display we are using today? Okay, so would the most advanced monitor use vector display? Do we only use raster display? Or does it depend on the brand? Some brands will give you the higher quality type of display, and others will give you the raster display. looks like you're not quite sure. Still voting. You didn't get the previous question right. Are you doing better this time? Okay. 21 answers. Once again, there is no clear answer. And once again, the correct answer is in the minority. Not doing well today. So nowadays, all display devices that you would be using are using raster display. Okay? Your screen is a collection of pixels. Okay? So whatever screen you are using, on your phone, on your tablet computers, it's all based on pixels. So it means that if you have a pixel-based image to display, it's instantaneous. If you have a vectorial graphic to display, first your computer needs to convert your vectorial graphics into a pixel image and then display it. Okay? And each time you zoom, it's converting back. Okay? So it takes a bit of time because unfortunately the display devices we have are not of the quality that we would like. Yeah. So we are using, unfortunately, raster graphics. Has it been always like that? Or was it better in the good old days? And we have just decided to go use a poor quality technology nowadays. Actually, in the past, vector displays was quite common. And it's still used in some devices that you may not be using. Okay? Here is a typical vector display. Okay? You have a beam drawing your graphics, and it's something continuous. Okay? It's not pixel based, it's just a beam and it's a completely continuous type of data. So if you are using an oscilloscope, you are using vector display. Okay? So some devices, again, each time it's in terms of space and quite complex devices, even if they don't do anything very clever, are based on vector display. Okay. In the past, there were some arcade games based on vector display as well. Okay. But the limitation of vector display in terms of technology is always a beam drawing what you are interested in, and usually it's monochrome. Okay, it has a very small thickness, so it's not really up to scratch to display the type of images we are interested in today. But I guess that in the future we'll go back to that because conceptually it makes more sense to use vector display. Okay, but most images are encoded using the raster format. And so we are going to look a bit at how images are encoded. So here we have a set of very simple raster formats. And all of those formats have what is called a magic number. Okay. And the magic number tells you what is the structure of your file. So if you have a magic number of which is P1, it tells you that it's going to be a black and white image. And that the encoding will be in ASCII. So human readable. If it's P2, it's a grayscale image, also in ASCII. P3 is going to be a color image, and we will go more into details. And then you have 3 formats, which are equivalent, but where the image is not encoded anymore in a ASCII format, but in binary in order to compress a bit the data. So here is a file. Okay, that's a complete image file. It's P1, so it means it's binary file. So you will get white pixels and black pixels. Okay, and so here is the size of your image.
So I thought P1 was ASCII.
Yeah, that's ASCII, 0 and 1.
Oh, you just said that was binary.
The values are binary,
Right.
because it's 0 and 1. That's correct. No, there's a bit of confusion. Yeah. So the values are binary. It's either black or white. So we use 0 and 1. But the way it's stored, it's using an ASCII format because we can read it. That's a good point. Very good point. So the format tells you it's P1. Okay, so we are expected black and white image. This one is just some kind of comment. So the software processing the image is not going to read it. Then you have the size of the image. So it's 6 pixels by 10 pixels. Okay, so a very small image. And then for each pixel, it's going to give you a value. Is it white or is it black? Okay, and that's how your image is going to look like. Okay. So now we have a P2 image. So similar concept, but now we can use gray levels. So instead of having either black or white, now we can use shades of grays. Okay. And so in this case, we are going to use 16 shades of gray, actually. Its values going from 0 to 15. Okay. And again, this image has a size 24 by 7. So if we display this, so number of gray levels go from 0 to 15. You can choose the number of gray levels you want, okay, but usually 250 is quite common, but here we are using just 16 gray levels. And that's how your image would look like. Okay? So let's have a look at the actual images. Where are they? Do you know that piece of software, iPhone View? It's very nice, free, and I would suggest using it for this week's activity. So let's put it here. Okay, so here I'm displaying my image, my FIP image. Okay, so you can see that standard image viewer like iPhone View can display it. You can see that it's based on pixels, so obviously it's all a bit fuzzy as soon as you zoom in. Okay, so we have seen about black and white and gray levels. So let's look at color. So in computing science, colors are created by a mixture of three different colors, mixture of red, green, and blue. Okay, or we can hear very often about RGB colors. So basically, we have those three colors, and we mix them in order to get more complex colors. Actually, any color which is in the visible spectrum can be expressed by a combination of those three. Okay? And if you put a maximum of red, a maximum of green, and a maximum of blue all together, you get white. Okay? If you don't put any red, any green, any black, any blue, you will get black. So it's maybe a bit different from what you have learned in maybe an art class, where you use primary colors which are different and the mixtures are different. So every color is expressed by a percentage, how much red, how much blue, how much green. So if you want a red color, a pixel with a red color, you are going to say it's 100% red, 0% green, 0% blue. If you want green, and you want not a bright green like this one, but something which is half saturated, you will just use 50% of green, and no red, no blue. If you want something which is gray, you will just have 50% of each of them. And each of those colors is usually represented by 256 values. Okay? So the values of the maximum of red will be 255, the minimum will be 0. Yeah? So it's 8 bits, okay, per color. So if we multiply the number of possible colors, we get more than 16 million colors. Okay? I don't know if we can differentiate between all those 16 millions, but at least that's what a standard color representation allows us to display. Okay? 16 million different colors just by mixing different values of red, green, and blue. So, which means that if you want to know what is the size of an image, so you know that you have 8 bits per color channel. So we have 3 channels, red, green, blue. So we have already 24 bits just for telling you what the color is for 1 pixel. And if you have an image H by W, you multiply it by 24 bits, and that gives you the size of your image. So for a very small image, okay, 640 by 480, I don't think you can get any camera with that level anymore, but that's what you have typically in the CCTV cameras in the street, so low resolution images. You have almost 1 megabyte of data in each image. Okay? So you can imagine that when you are creating a video, the size are increasing very fast. Okay, so in order to illustrate further how you will create colors, so here you can pick different values. So if I pick this one, you can see that it's full green, but I have a bit of red and a bit of blue. Okay, so it's not a pure green. You can also notice that we have 3 components. Okay, and you can also express it in hexadecimal format. Okay, because here we have values because we are using the decimal format, which have from 0 and 3 characters. If you use the hexadecimal, all your values will fit within 2 characters. Okay, so it means it allows you to specify the colors just with 6 characters. And that's what is used typically in HTML pages. So when you are doing your CSS and you want to express a very specific color, you will use the hexadecimal format. And a software like this one gives you the correspondence between the hexadecimal and the different colors. So here we can see that pink, for example, or that kind of pink, is a mixture of red and blue, no green whatsoever. Here as well, you can play with the different colors, and you can see how the hexadecimal is changing when you have those different mixture of colors. So when you are using an HTML page and you want to use different colors, so one way is to use this hexadecimal codes for getting the exact color you are interested in, or you can use pre-defined colors. Okay, you can just use the name of the color. So it understands standard colors like black, white, red, and blue, but it has a whole range of colors which have been predefined. Okay, like Navajo white. Okay, I don't know if anybody knew about Navajo white before. So you have already a large range of colors that you can pick, but as you know, you can create 16 million of them. So the large majority don't have a name, but you can define it yourself. And using this hexadecimal code, you can get the exact color that you wish to get. Okay, so now if we move back to our file, so now we have the file of type P3, okay? So it means it's going to be a ASCII color file. So here we have an image which is 3 by 2, so a small image. And I'm going to use up to values up to 255 to express each color channel. Okay. So here it's an image 3 by 2, so I have obviously 6 pixels. So here I have my first pixel, which is 255.00. So what is the color of that? Red. Yeah, so that's going to be a pure red pixel. Then I have a pure green and a pure blue pixels. And then I will have some mixtures plus a white pixel and a black pixel. Okay. And that's how I define that image. Yeah. So you can see that a color image takes 3 times the size of a gray level image because you have 3 channels instead of 1. And then when we move to the non-ASCII format, the binary format, so you can still read the header. Okay, so here we have a P6, which means it's going to be a color image. Here is the size of my image. Here is how many levels I will have for each channel. And then I have my values, which have been encoded in a binary format in order to take less space, and it's not human readable. Okay. And in practice, that's the format which are used, the non-human readable ones, because they take much less space than the other ones. Okay, so if we take that file, we know that we have 255 values, which can be encoded with 8 bits, which is equal to 1 byte, which means that for each pixel, which has 3 color channels, we have 3 bytes. Then we have, that's the size of the image. And if we multiply that by the 3 bytes, we get already 4 megabytes for the size of that image, coded in colors. And then we shouldn't forget the header. Okay, so there are, in this case, 17 characters, which add up a little bit on the image. So the header is not counting much for the full size of the image. But you can see that that's a megapixel image, and we are already at 4 megabytes for storing it. Okay? And 1 megapixel image, again, nowadays, that's not much compared to what you have on your cameras. Yeah. So it means that it's not acceptable to have images which take so much space. So we have seen some very basic raster formats. Okay, so that's a very simple one where we can understand everything which is going on. But there are many others. Okay, and I'm just going through a few of them for you to understand why should I store my file as a JPEG instead of a TIFF or a GIF. Okay, you have all those formats. Why would you choose one instead of another? So one of the popular ones is the tagged image file format, or TIFF. And this format was created for printing images. Okay. That was designed so that when you print it, you get the best possible quality. Then you have the graphics interchange format, or GIF. So that was designed to display images on the internet. Okay. It's for on-screen viewing. It's not good for printing. You will not get very good quality. But for viewing on a screen, it's pretty good. It's very good for most images, except when you scan a photograph. Okay, or for a photograph, GIF is not doing a very good job. So obviously, you needed a format, a digital format for photograph, and that's what JPEG is about. Okay. So it has been designed to display photographs over the internet. Okay. It's not good for vector drawing. Okay. We have already seen that. It's not very good for text because everything looks blurred. Or for lines, so if you have a design which is cartoon-like, black and white, it's not going to do a good job. Everything will look blurred. But it's very good for photographs. And typically your cameras take JPEG photographs. Yeah. And it's very bad for printing. And then you have the PDF format. And it's one of the good things of PDF is that it can handle vector and raster graphics. Okay? So if you have a PDF document and one image was based on vector graphics, you can zoom as much as you want, you will get good quality. But if the image was encoded initially as pixel, it's going to be rubbish anyway. Okay? So just to clarify that the way you save your files, is very important, and it really depends on the application you have in mind. So the thing is that all those formats try to find a clever way to compress your data. Okay? Because we have seen already that just a megapixel image is going to cost you 4 megabytes. Okay. If you start doing videos or having hundreds of images on your device, it's not going to fit. So you need some tricks to compress that image. Okay? And all of those formats use different tricks. So there are the tricks which allow you to be able to print something pretty, but not very nice on your screen. The tricks which are very good for text or for images which are not photographs, and the tricks which are very good for photographs. Okay. So, as I said, we are mainly working in the raster world, so we need to encode all those pixels, and it takes a lot of space. Okay. Obviously, it takes a lot of space, which is a problem of storage, but it's also a problem of opening a file. You need to read it. So if it's a huge file, you need more time. It's especially an issue on the internet. You don't want to have a website where people click on it and you have to wait 10 minutes to get all the images to load. Yeah. So I gave you the size for a very small image. What about a video of 1 hour? How much space would you need? 80 gigabytes. If you don't compress anything. Okay. So that's if you keep all the information you had from the start. But maybe some of you are aware that the standard film that you may legally download from some place will be around 1 gigabyte. Yeah? And a standard film is more 130 minutes, 2 hours than 1 hour. Okay? So it means that something which should, and that's a very small image, yeah, 600 by 480, where we are speaking of gigabyte, mega size images for your film. So it means that there's been a strong compression from hundreds of gigabytes to just 1. Okay, so how is that feat performed? How can you compress something which is 100 to 1? And that's what we are going to see in the rest of this lecture. So how to reduce the size to describe an image. So there is a process. So you have your initial data, which I assume are the pure data. Okay, no information has been lost. And then you are going to have what is called an encoder. So you are going to use a set of tricks in order to reduce the size of that image. And now you have a small image or a small video. You can store it or you can send it through the network. And once you want to display it, you have to do the opposite. You have to use all those tricks back to recreate the original image. Okay? That's why it had a bit of delay, because each time you are getting an image, first is going through the network through one format, and then you have to reconstruct it. Okay? And there are two families of compressions. Okay? So there is what is called the lossless compression. So you have something big, you squeeze it, and then you get it back to its initial form. In the process, you haven't lost any information. Okay? So that's the lossless compression. But you have also what is called the lossy compression, which is to say, okay, in order to compress it, I'm happy to throw away a bit of my initial data. Okay? Initially, I had 16 million colors. Nobody can see 16 millions. Let's squeeze it to a reasonable number. Nobody will notice the difference. Or maybe they will. Okay? So in the lossy compression, you say, there's too much information. We don't need all that information. Let's throw a bit away. Yeah. So when you are using a compression algorithm, you will get a compression ratio. So what is the size of your image, your video before compression, and what is the size after compression? Okay. So basically you want a high number. Okay. Can you compress by a factor of 10, 100? Okay, so I have defined two types of compression, lossless and lossy compression. Let's imagine that I want to send an executable, okay, which can be quite a big file. So I need to compress it. So what type of compression do you think I should use? Should I use the lossy compression, because that's what is going to compress the most? I am going to use the lossy compression but the risk is since I've thrown away a bit of data, my program may not work as well as before. Or if I use lossy compression, my software is not going to work anymore because I've thrown stuff. Yeah? Any more votes? Okay, let's see. Yeah, again, there is no no clear information. Okay. Fortunately, this time the highest percentage is the correct one. So it's the third one. Okay. If you use lossy compression on an executable, your file is not going to work anymore. Okay. Every single bit in an executable is important. It's not like in an image. Okay. If you have a bit of the image which has been removed, or if you have converted an image from color to black and white, that's a compression. You had 3 channels, you have only 1 left. So the quality has gone down, but it's still an image that you can use. Okay. In an executable, it's not possible. Okay. If you throw something from your piece of code, your code is not going to work anymore. Okay. If you have the if statement and you remove the if, your code doesn't make any sense anymore. Yeah. So you cannot use lossy compression on an executable. Okay. You must use a lossless one. So in lossless, the data at the end of the process are the same as the data at the start of the process. Okay? It's just a problem of packaging in between. So if there is redundancy of your data, you remove them during the compression process, but there is a way to bring it back when you need to use the piece of software. Okay? So typically, lossless compression is used in computer programs, but it's also used in legal and medical documents. Okay? Because for legal reasons, if someone has signed a contract, you cannot say, yeah, I give you another contract. Oh, it's roughly the same, I've just removed a few things. No. Your lawyer is not going to be happy. You sign that one, you want that one. Okay? You cannot change any single bit. Very often it's the same in medical documents. Okay? They are very critical data, and you cannot trust a software to remove stuff because it believes it's redundant. So a typical lossless method is zip. Okay? You create zip files. It compresses your file, hopefully. You send it, and you unzip, and you get your file back. So lossy coding is really more when it has an aspect which is kind of subjective. Is, yeah, it looks nice. Okay, so it's something subjective. You can remove a bit of color, a bit of things, so it's a bit more fuzzy, but still looks nice. Okay, so it works very well for images or for sound. Okay, like your MP3 player. That's lossy compression. A lot of good notes have been thrown away. Okay, so just to show quickly how it works. So here we are looking at lossless compression. So it's called the run length coding. Okay. When you are encoding your data, sometimes you want to encode some information like this one. Okay. So instead of having all those characters, you can just say, no, actually I have 9 B's, 16A, 1N, and 10N. And you haven't lost any information. From that, you can fully reconstruct this sequence. Okay, so when you have your black and white images, if you have one corner of your image where everything is black, you could say, oh, all those values are zeros. You know, there are 100 zeros. And then you have a bit of 0, a bit of 1. But using that type of techniques, you can compress seriously a file if the file has the right properties. Okay? Because some files have never had that type of sequences. So that compression is not going to work on it. But for many types of files, it works well. So, for example, for our initial binary file, binary in terms of black and white, you can see that it's full of zeros. Okay? So to encode the image, instead of using all that, I could say it's 4 white, 1 black, 5 white, 1 black, 5 white, and so on. And actually, we know that when it's not white, it's black. Okay? So I can remove the W and the B. So I can just say it's 4 of the first type, 1 of the second type, 5 of the first type, and that's my new encoding. So initially I had 120 bytes, now I have only 38 bytes. So I have reduced the size of my file by 3 without losing any information whatsoever. I can fully reconstruct this file from that information. Yeah? Is that clear? So that's a very simple type of compression. Okay? Nothing very clever there, but it can be highly effective if the image has the right properties. So images which have the right properties are technically text. Okay? A text is a white square with a bit of black dots here and there, but it's roughly something white. Okay? So obviously using that type of compression is likely to work very well on text. May work very well on that type of cartoons as well. Okay? It's just a line-drawn cartoon. So basically it's a white object, a white graphics with a bit of black here and there. Okay? So for that type of images, this RLC compression algorithm is going to be working very well. So that's the first baby step inside the compression world. Now we are going to look at an algorithm which is a bit more advanced, that some students find a bit difficult. So if you have, feel free to stop me and ask me questions. The idea is very simple. We know about the ASCII format, and we know that each character is encoded using 8 bits. Actually, we need only 7, but since computer works on an 8 bits minimum size, it uses 8 bits. So each character is encoded with 8 bits. Yeah? But you could argue that in English, the character E is quite frequent, and the character Q is not very frequent. Okay, many texts will not have any Q. Yeah. So is it reasonable to use as much bits to encode the two? Would it not be better to say, okay, since there are a lot of E's, I'm just going to encode them with 5 bits. There are very few Q's, so I can afford to encode it with 10 bits, maybe. Okay. In average, it's going to be a very good deal because there are a lot of E's and not many Q's. Yeah. So that's what the Huffman coding is trying to do, is to say, we are not anymore for the equalities between all the letters. Okay? Some letters count more than others. So for the important one, we want small encoding. And the cost is it will be very long encoding for the letters which are quite rare. But it doesn't matter because we are not going to use it much. Okay? So you could have an encoding which is based on a language. You can say, yeah, in English we know that E is frequent and Q is not very frequent. So you could have an encoding once and for all. Okay. But Huffman coding is even more powerful because each time you encode a document, it will create a specific encoding for that document. Okay? Because if you are working for some specific football clubs, Qatars is a word which will happen very often. And Q is quite important. Okay? And maybe it wouldn't be a mistake to use a long encoding. So in this Huffman coding, there is an analysis of the document you want to encode, and will tailor the encoding to your document. Okay? So let's have an example. So here we have a text. Okay? So I just want to encode that text. The first thing that happens in this algorithm, I'm going to count how many times each character is found in my text. Okay, which one is the most frequent and which one is the least frequent. So if we look at that text, we can say that space is really an important character because I have 7 of them. On the other hand, the letter X, I have it only once. And you can notice that in that text there's no Q, actually. So we are not going to bother to try to find a way to encode Q because we don't need it. Okay? So we are just going to count our letters in order to know which ones are the most important and which ones are the least important. Yeah? So then, what we are going to do is for each letter, we are going to put the number of times we have counted them. And now we are going to group letters according to their frequency. Okay? So we are going to say, oh, the least frequent letters are O and U. So are we going to bring them together? Okay? Then we are going to say, oh, X and P are also very infrequent. We bring them together. R and L are very infrequent. We are going to bring them together. So now we know that this group of letters have a frequency of 2. Okay? And those letters have frequency of 2 as well. So we carry on the process and we say, oh, here we have a letter of frequency of 2, and this group of letters have a frequency of 2, which is in total a frequency of 4, which is not very high, so we bring them together. Okay? So basically we are building some kind of tree, starting by combining stuff which is not very frequent. So you are going to step one after the other, and you can see that the infrequent letters are going to be at the bottom of my tree, and the most frequent ones are going to be at the top of my tree. So step by step, I am combining, always taking the least frequent ones, until the last steps, where I have a tree representing all my letters. Okay, I had 36 letters in my sentence. At the bottom of my tree, the leaves, the lowest leaf, I have letters which I've been counting only once. And the letters which are the more frequent, like the space, is very high in the tree. Yeah. And then we have the 4, which are in the middle of the tree, and so on. Yeah. So here is my tree with all my letters. And now we are going to design a specific encoding to represent that tree. And it's very simple. You start at the top of the tree, and when you go to the left, it means that the encoding starts with a 0. You go to the right, it means the encoding starts with a 1. Okay? So if I want to encode T, I need to go left, right, right, left. Yeah? So it means that my T needs 4 bits, 0, 1, 1, 0, in order to be encoded. On the other hand, in order to encode my space, I just need to do right, right, right. So I can encode it with 3 characters, 1, 1, 1. And a letter like X, that is very infrequent, I need to go right, left, left, right, left. So I need 5 characters to encode it. Okay, so we can see that the most frequent letter needs only 3 characters for being encoded, and the least important one needs 5 letters. Okay. So now I can replace every single letter of my text by the corresponding code. Okay. So instead of having my 8 bits initial for each letter, now I will have sometimes 3, sometimes 4, sometimes 5. So if we look at a smaller example, so I have E, which is coded by 1, 1, A, which is coded by 0, 0, E, 1, 1 again, B by 0, 1, 0. And the beauty of this code, I don't have to tell when a letter starts or finishes. So I start reading, and I say, oh, it starts with 1. So it can be either a D or an E. Yeah? Or there is a 1 afterwards, can only be an E. That's the only letter we start with 1, 1. First character is an E. So now I go to the next character. Start with a 0. So it can be A, B, or C. Another 0. So it can only be A. Next character. Again a 1, 1. Then I have a 0. So it can be A, B, C. I have a 1. Oh, it can be either B or C. Third character is a 0, so it's a B. Yeah? Got it? So you can see it's quite a very clever way, because we don't have to make the difference between here is the code for 1 pixel, here is the code for another pixel, or for a letter or another letter. The way it has been designed, you exactly know when it ends, and you customize it to your data. What is very frequent, you use short codes. What is very rare, you use long codes. At the end of the day, you will compress significantly your data. So you can see that my initial text in this case had 10 bytes, because I had 10 letters. Now I have only 22 bits. 1 byte is 8 bits. So I have fewer than 3 bytes. Okay. So I have compressed my document by a factor higher than 3, just a bit higher than 3. Okay. Another technique, and we are not going to go into the details because it's becoming more and more complex, but the idea is a bit similar. But instead of focusing on letters, Now it's focusing on words. You know, THE is very frequent in English. So let's code THE with a few bits. And a very long word, which may be very rare, let's code it with a lot of bits. Okay? So it's the same story as before, but instead of focusing on letters, now we focus on words. Okay? The algorithm is quite different, and I will provide the full algorithm in my slides, but just for your interest. Okay? If you're interested, look at it. If you are not, just go to the next one, next slides. Okay. So here is a set of images. And you can see that images have different properties. So we have one color image. We have 3 black and white. We have a black and white image. I mean, not black and white, gray level image. We have a gray level image, which is quite busy. And we have a gray level image where you have backgrounds which are quite monochromous. Okay, so they have different properties. So depending on the algorithm you will use in order to compress, you will get different compressing ratios. Okay. The 2 previous algorithms, I explained how to use it for letters, but you can use it for colors as well. Okay, same story. So here I've used 3 types of algorithms in order to compress those 4 images. So the first 2, so that's the one based on words, and this one is a improved version of the one we have just seen, the LZ77, and then we have the Huffman coding, which is based on letters. Okay. And interestingly enough, when we use the story about words, for 2 of the images, the compressions has made our file bigger. Okay? Because those 2 images, so Lena and the flowers, have quite a busy background, so there was no repetition in it. So it created a complex code and stuff, but at the end, it costs more to use that code to just the basic RGB format. Okay? So that's why we have compression ratio of 0.86, 0.87. So after compression, my file is bigger. So you need to be very careful when you are compressing files. Sometimes they get bigger, so don't use your compressed file, better to send a normal file. Okay? When we use the improved version of that algorithm, you can see that eventually the compression ratio is moving just above 1. Okay? For those 2 files, which looks quite difficult to compress. Okay? And when we use the pack Huffman coding, again, the compression ratios of those 2 files is quite poor. On the other hand, when we look at the picture with the aircraft, you know, you have a nice background. I guess it's blue sky. The aircraft itself, you know, has quite a unique color. You can see that we can reach compression of 3, you know, 3.1 or 2.2. The football one, again, there's a bit of grass here and there, so there's a bit of repetitions. So a bit of compression will work. Okay, but you can see that the rates of compressions are not fantastic. Okay, and also you can see that there's not one algorithm which is always better than the others. It's really a combination. For that type of image, that's the best algorithm. Okay, so that's about lossless compression. Okay. We haven't thrown away any information. All the information is still there. We just presented it in a different manner. Okay? Looking for repetitions or frequencies of certain terms. So now we have the lossy compression. So now we want to transmit data, and what is important is that the output is nice. It's not perfect, it's just nice. Okay? So that's typical when you are working with images, videos, or sound. Okay? Here we are going to focus on images and sound. And so there are three very important compression algorithms. There is the JPEG one we have seen already. So that's about images. Then we have the MPEG one. That's one is for videos. And then we have the MP3 one, which is for audio files. Yeah? But the three are very similar conceptually. So let's have a look at the JPEG encoding. So what JPEG is going to do is to take your original image and create some small blocks, 8 by 8. And each of those blocks, JPEG is going to try to simplify them. Okay? And I think the next slide is the best way. Is the JPEG consortium, using some advanced mathematics, have found that any block, here we are speaking about grayscale, but there's equivalent for colors, can represent it as a mixture of those 64. Okay? Any image 8 by 8 will be a percentage, so it's going to be 5% of that, 2% of that, 1% of that one, 0.23% of that. So you combine all those 64 and you get back your image. Okay? And so what the JPEG idea is, okay, my image is a combination of those 64. And in some images, it's going to be 90% of that one, 5% of that one, and almost not point something of the others. Which means that for a human, you are not going to see the added value of the other 62. You are going to say, yeah, it's 90% that, 8% that, and I throw away the 2%. Okay? It's not going to change dramatically the image. Okay? So that's what JPEGs do. It cuts your image in blocks of 8, express the image as a collection of these 64 patterns. Until now, no data has been lost. It's just represented in another way. And then you say, yeah, but I want my JPEG to be very compressed. So out of the 64, I just keep the first half. And you are losing a bit of information. But if the first 32 are representing 95% of your image, you are not losing much details. Okay. So here, if you can look at this image, you can look here the percentage of data which are kept. Okay. So you can see that here I'm at, when I'm reaching something like 40% of the data, adding the extra coefficients don't affect the quality of the image. Initially, when I use only one coefficient, it's rubbish. When I use two, it's rubbish. But after a while, the quality of the image is pleasing enough, and I don't have to use more. Yeah? Any question about that? So you are just removing the least important coefficients because they don't give much information about your image. So that process of removing coefficients is called quantization. Okay? So when you are using a JPEG encoder, they ask you how much of the image you want to keep. You want to keep 90% of your initial image. Okay, we make sure that we keep the coefficients which keeps 90% of your data. Okay? So for some images, you are going to compress a lot. For some images, you are not going to compress a lot. Because if all the coefficients have the same values, you are not going to remove any, because they are all important. But if some coefficients are in the 20% and some are the 0 point something, you can remove the 0 point something. Okay? So when you are compressing with JPEGs, you can have two questions. How much of the image you want to keep? 90%, 80%? Or what is the size of the image you want at the end? Okay? And they are going to remove all the coefficients you need to get that size. But the results may look really rubbish if you are really aggressive in your compression. Okay? But it means that here you can really get the size you want with JPEG. And obviously you are going to use this lossy compression, where you are going to remove a lot of stuff, but then you can still use a lossless compression. So you can do the second compression step using the method we have seen before. So you can combine those to get even better compression rates. Yeah? Everybody happy with JPEG? No question? Let's call it happiness. And then we have the MPEG encoding. Okay? So JPEG was for people into photography. MPEG is for people into movies. Okay? The idea is, what is a movie? Is just 24 images, or 30 depending on the standards, which are shown in 1 second. Okay? So it's just a collection of images. There is nothing else. Okay? So what it means is, first you can do JPEG on each image, and that will allow you to compress your movie. Okay? So that's called spatial compression. Okay? You have an image, and within the space of the image there is redundancy, and we have seen that we can either remove or compress based on this redundancy. But then there is what is called the temporarily redundancy. An image, a video, when you look at the first frame and the third frame, usually not much has changed between the two. Okay, very tiny differences. So that's another opportunity for compression. Saying, oh, image 3 is basically image 1, and just move the car a little bit from here to there, and nothing else. Okay? So if we look at those two frames, so imagine a video which is shot from a car window. Okay, so what has changed between the two images? You know, the field is still at the same place, the house is still the same. Just look that the tree has moved from next to this window a bit further to the right. Okay? I mean, if you look at the two images, you could say, why would I bother saving those two images? I just save this one, and I say that the next one is the same where I move the tree. And I get quite a reasonable new image. Okay? So here are the differences between the two. So when it's gray, it means that the difference is minimal. And when it's black or white, it means that there are serious motions. Okay? Which means that what I'm really interested to store is those differences. The rest, if I want to compress, I can say it's just the same. Yeah? So when you are dealing with movies, you can compress at two levels. One is between frames, saying, yeah, they are quite similar. There is redundancy between those frames, or within each frame. Okay? So what MPEG does both, obviously. So first of all, you use JPEG for each single frame. And then when you use MPEG, you just try to decide what you are going to say is actually between that frame and that frame, I can interpolate. Okay, what is in the middle is kind of average of this one and that one. Okay, here is a tree here, here's a tree here, in the middle the tree is going to be in the middle. Okay? So that's the concept of intraframes and interframes. So the intraframes are the frames that you are only going to use JPEG. But for the frames in between, you are going to interpolate between the one which have been used using JPEGs. You are going to say, the I ones, I store them properly, properly using JPEG. The P ones, I'm just going to say, interpolate between those, and you will get something decent. Okay, so you have a double compression. And obviously, the most intraframe you are using, the less you are going to compress. Okay, because if you say everything is intraframe, you are just using JPEG. If you say I take one frame every 10, you are going to compress quite a lot, but obviously your quality of compression is going to go down. Yeah. So that's what I wanted to tell you about JPEG and MPEG. Okay. Do you have any question on that? No? So let's play a bit with R-Font View, because I like it, and I will ask you to do that during your assignment. So here I have an image, and when I save my image, it tells me which format do I want to use. Okay? So typically JPEG is the standard one. And now I can say, what quality do I want? Do I want 80% of the information? 10% of the information? I can choose. Okay? So you have seen my original image. Let's save it with 50% of the information. So let's save it as desktop 50%. And I go back to the original image and I save it aggressively 10%. Okay. So my initial file had a size of 4 megabytes. The one I saved at 50% has a size of 100K. So I've already improved by 40. The other one $28K. So I divided again by 10. Okay. So now we want to see the quality. Yeah. What has been the effect of that JPEG? So let's start with the 50%. Still quite a pleasing image. So that was the original one is here. So that was my initial image. Now we have my 50% JPEG. I have compressed it by, we said 100? Or was it 10? 100? I'm not following. So we started at 4 megs, and now we are 100K. So we divided by 40, and we still have an image which looks quite nice. Yeah? Now, if I look at my image, which one is a 10%? Here, you start seeing the pixels. Yeah. So you can see that it has become quite aggressive, and now visually the quality has gone down. Okay. But by removing 50% of the information, it still look okay. Okay. So it depends really on your application, what you want to do with it. Okay. But something which is very important is then imagine you are an artist or you are creating a graphic. When you save your data, don't compress it lossily. Because if you save it at 10%, the information lost, you will never come back. Okay? So each time because often you work on a piece of graphics, you save it, you open it again, you change a few things. See, each time if you use JPEG, each time you are throwing stuff away. So after a few times, your image is rubbish. You cannot edit it anymore. Okay? So it's very important that when you are working on an image, initially don't compress it using any lossy compression. Okay? Once you have finished with it, and you want to put it on your website, send it to people, put it on Facebook, you can compress. But keep the original without removing anything. Yeah? So in activity 16, we are going to focus on images and videos. I think they are the most interesting ones, and that's the one practically that you will need to master. So I'm going to provide you with 2 images, and I will ask you to do some experiments, like what we have done. I will ask you to compress it in different ways, with lossy, with lossless, with different ratios, and you are going to tell me what is the size afterwards, what has been the compression ratio, and what about the quality. Maybe one image you can afford to keep only 20%, and another image you cannot afford to lose more than 50%. Okay, so it really depends on images as well. So that's what will be the first part, where you will be doing some experiments. You can use our font view, I provided the link, but if you want to use any other software, you can do it as well. I mean, JPEG compression, most graphic software will allow it. And then I will ask you to think a little bit, because now you have a basic understanding of how compression is done when we are looking at the lossy one. So that's the interesting one, because the output is different from the input. And I'm going to show you some extreme compressions in terms of JPEGs and in terms of MPEG. And I want you to try to explain to me why it looks so bad. Okay, so just to give you a taster, here is an image which has been compressed, a video which has been compressed aggressively using MPEG. Okay, so you are going to analyze it, and you are going to tell me why it's so bad. Okay, what kind of effect, knowing how it's compressed, you can guess what would be the effect. Okay, so is it the JPEG the problem? Is it the fact that there are too many intraframes? So you interpolate between things which have nothing in common, for example. Okay, so I want you to analyze. So I'm providing you with a couple of videos to look at, and I want you to have a critical look at them and tell me why it's not good, okay, according to what we have seen. So thank you very much for your attention, and I will see you